So who's familiar with Towers of Hanoi? Also called Towers of Hanoi.
Can I have a question first?
Sure.
You gave the example of a Fibonacci that's a recursive program, and then you gave a non-recursive program. Is there a name for that?
Just non-recursive, I guess.
Okay.
There's probably a better name. All right, so Towers of Hanoi. You have a series of disks. My disks happen to be square, but I'm still going to call them disks. And they're different sizes. And the idea is you've got 3 pegs, and you're going to put disks onto one peg. And let's put 3 disks on here. All right, so I've got a small one, a medium one, and a big one. And the goal of the game is to move the disks from one peg to another peg.
You can't really see them.
Beautiful display. There we go. All right. So we got small, medium, and large. And the goal is to move the 3 disks from one peg to another. And you have to follow a few rules. Okay, so you can only move one disk at a time. You can only move a disk that's on the top of a pile. And you can't put a large disk on a smaller disk. Okay, so if I want to move these 3 disks to another pole, right, I can take this and move it somewhere. Well, I can move this again, but that's not going to do anything. So this is really the only option I have to move, and I can't put it on this pole, so I'm going to put it on the 3rd pole. And now I'm going to put this one over here, and I got to move this big one right here. And then move that over there, put the middle one in the middle, put the small one on top. And I've succeeded. So did you count how many moves that took? Actually 7. That's close. So 7 moves to move 3 disks. And the more disks you have, the harder it is to do this. Now if you only have 2 disks, and I want to move this from here to say here, right? I can move that, and I can move this, and I can move that, and I'm done. So let T of n be the number of moves to move n disks. So T of 3 was equal to 7. T of 2 was equal to 3. T of 1, what do you think that's equal to? If I only have one disk, I just want to move it from one pole to another. How many moves does that take? It takes 1 move. Just pick it up, put it somewhere else. So T of 1 is equal to 1. So any theories what T of n is in general? Kind of looks like 2 to the n minus 1. All right, anybody want to try this with 4 disks? It's going to take you 15 moves. But there's limitless fame and glory on the other side if you succeed. Or a...
Quite an enticement.
Yeah. Anybody want to try it? Okay, come on up. Do you know how to do this ahead of time? Okay, that's okay.
What, are we bringing in a ringer here?
Yeah.
I'm going to get it to a specific pole, or?
Nah.
Move it over so we can see what you're doing,
yeah,
so we
yeah.
can criticize.
That's 7 moves.
8.
8. You're good. Cool. Awesome. Okay, so that took 17 moves, but I think there was one misstep in there. But you can actually do it in 15. I'm not going to embarrass myself by trying to do it. So we'd like to prove that you can move n disks in 2 to the n minus 1 operations. And it's actually a pretty straightforward proof. So let's repeat. 1, 2, 3, 4, 5, 6, 7. Okay, after 7 moves, what have I done? I've moved everything except the biggest disk to another pole. In other words, I just solved the problem for n minus 1, which we know takes 2 to the n minus 1 minus 1. So we've just done 2 to the n minus 1 minus 1 moves, right? And this moves n minus 1 disks. Now I need to move the biggest disk onto the destination pole. So that takes 1. Move largest disk. And then I have to move the same n minus 1 disks onto that pole. This is the part where I would like to embarrass myself. I'm going to try this blind. I like that. All right, and that also took 2 to the n minus 1 minus 1. So the number of moves for n disks is 2 to the n minus 1 plus 1 plus 2 to the n minus 1 minus 1. Which is equal to, well, 2 to the n minus 1 plus 2 to the n minus 1. That's 2 times 2 to the n minus 1. What's that? That's just 2 to the n. And then we have minus 1 plus 1 minus 1. That's just minus 1. As long as we know that t of n minus 1 is equal to 2 to the n minus 1 minus 1, we can show t of n equals 2 to the n minus 1. So this is another inductive proof, right? Our proposition for n is that to move n disks takes 2 to the n minus 1 moves. And we actually showed that if the proposition is true for n minus 1, then it's true for n, right? But we could do it more properly. Given p of n, so t of n equals 2 to the n minus 1. T of n plus 1 equals number of moves to move n disks plus 1 to move the middle disk plus the number of moves to move those n disks again, 2 to the n minus 2 to the n minus 1 plus 1 plus 2 to the n minus 1, which is 2 to the n plus 1 minus 1 plus 1 minus 1. So that's a straightforward inductive proof for the number of moves required. But again, it gives us an algorithm. So I have 7 disks here. If I want to move all 7 disks, if I know how to solve this for 6 disks, it's trivial. If I want to move all 7 disks from here to this post on the end, all I got to do is move the first 6 disks to the spare post, and then take 1 move to move the biggest one, and then move these 6 disks to the target post. And I've solved it for 7. And you can do that for any number of disks. And that codes really easily also. So I have a function called tower, and tower takes 4 arguments: the number of disks, the number of the post you want to move from, the number of the post you want to move to, and then a third number, which is just the spare post, the one that you're not using. So if I call tower 8, 1, 2, 3, it'll move 8 disks from peg 1 to peg 2, and I'm telling it peg 3 is the other post. You can figure that out with a formula, actually. And I'm counting the number of moves required. And here's my base case. If the number of disks is just 1, just move it from the from post to the to post. And move is just a function that prints out move from this post to that post. Otherwise, let's move num minus 1 disks from the from post to the open post, and then move 1 disk from the from to the to, and then move num minus 1 from the open that we moved it to up here to the target disk, the target post. And move just prints out what we're moving from and to. So if I call this for 4 disks, right, there's the solution for 4 disks. So move from 1 to 3, move from 1 to 2, I've got 1 on my left here, move from 3 to 2, move from 1 to 3, move from 2 to 1, next line, move from 2 to 3, move from 1 to 3, move from 1 to 2, move from 3 to 2, 3 to 1, bottom line, move from 2 to 1, move from 3 to 2, move from 1 to 2.
I think it's supposed to be 1 to 3.
1 to Oh, I messed up, man. Anyway, you get the idea. Right, so it'll get you there. So the legend of Towers of Hanoi is that there's a cave somewhere, and there are 64 discs made out of jade, and there are monks who are just moving these discs from one pole to another endlessly. And they started with all 64 discs on one pile, and their task is to move the discs to another pile, and when they finish, the universe ends, basically. So that's what's going on in the cave. And so the question is, how long do we have until the universe ends, right? And if they move 1 disk per second, we've got, roughly 2 to the 64th seconds, which is a really long time. So there's 2 to the 64th. If we divide by 3600, that gives us the number of hours. If you divide by 24, that's the number of days. If you divide by 365, that's the number of years. So it's a good, safe amount of time. But we can find the solution for 64 disks. Right, there it is. If you do those, it'll move a stack of 64 disks.
I'll try that this weekend.
Yeah. Start early. All right, so induction and recursion and recursive functions all kind of tie together. And the interesting thing for us as computer scientists is the fact that sometimes the inductive proof actually gives you an algorithm that you can write as a piece of recursive code to solve your problem. So how many people took a stab at the homework questions? So let's just try this one. This is a different kind of question. And I think the odd questions, the solutions are in the back of the text. So you can refer to those if you're stuck. But let's prove n times n plus 1 times n plus 2 is a multiple of 3 for all n bigger than or equal to 1. So let P of n be the proposition n times n plus 1 times n plus 2 is divisible by 3. And let's prove this for all n bigger than or equal to 1. Well, P of 1 says 1 times 2 times 3 is divisible by 3. And clearly it is, because we've got a times 3 right there, right? And if we do the work, this is 6. 6 is divisible by 3, so this is true. So given P of n, prove P of n plus 1. I haven't done this yet. I hope I know how to do it. So let's, P of n is given, which means n times n plus 1 times n plus 2 equals 3 times some integer. Right, that's what it means to be divisible by 3. Where can we go from here? That's code for I don't know exactly how to do this.
I can't remember exactly what I did, but I broke it up into 3 cases.
Okay, that will definitely work.
That's what I did.
I'm wondering if there's a way with just one case. Did you try multiplying this out by any chance? So let's try this. Let's multiply this left side. So just doing algebra on the left side, we should get n cubed plus 3n squared plus 2n is equal to 3 times some integer. And then let's see what P of n plus 1 says. It says n plus 1 times n plus 2 times n plus 3 is divisible by 3. So let's multiply this out. So n cubed plus 3n squared plus 2n plus 3n squared plus 9n plus 6. So this is what n plus 1 times n plus 2 times n plus 3 is.
I think I did what I think was a little bit easier way.
Yeah, you basically used modulo 3, right?
No.
Because you had 3 cases.
No. I used a theorem from number theory
Mm-hmm.
that says if you have a number dividing a product, then the number that's dividing has to divide one of the factors if and only if the number that's doing the dividing is prime.
It's prime, right.
If it's not prime, then that won't work.
Right.
So I broke it up into 3 cases where n, or 3, has to divide one of those 3 things.
Okay.
And then
if it divides n, it also divides n plus 3.
it's
And if it
easy
divides
after
one
that.
of these, then it divides. That's cool. That's very cool.
But doing it like you're doing it now, to break it up into, probably you can still do it that way, but just bringing a lot of cubic stuff.
Yes, yes. But this is the inductive route, right?
Right.
So we want to show that this is divisible by 3, and we know that this is divisible by 3. Any ideas how to get from here to here? We've done something kind of like this before.
Just break.
Basically. So yeah, this is the adding 0 thing. And I know that this thing is a multiple of 3, so let's rewrite this as n cubed plus 3n squared plus 2n plus, we need another 3n squared, and we need another 9n, and we need a 6.
But that part is divisible by 3 too.
And we know, yes, so this is 3 times k, and this is 3 times n squared plus 3n plus 2, which is 3 times k plus all of that stuff. Therefore, 3 divides this, and that gets you Pn plus 1. And then you just throw your induction quote at it.
I mean, the way I did it, I still use mathematical induction.
Right, so here's what Randy did if you didn't hear it. And I don't think we talked about this, but the fact is that if 3 divides a times b times c, then 3 divides a, or 3 divides b, or 3 divides c.
But only because 3 is prime.
But only because 3 is prime, because 4 will divide. That's not a good example. You can find counterexamples. 6.
4 times 9 is 36.
Yeah, 6 divides 2 times 9, but it doesn't divide 2 or 9. But if you think about unique factorization of this product, since 3 divides it, right, we can write this as some power of 3 times other stuff, and one of these has got to be divisible by 3. So if you use this fact, right, then you have 3 possibilities. 3 divides n, or 3 divides n plus 1, or 3 divides n plus 2. And if 3 divides n, then 3 divides n plus, if 3 divides n plus 1, it divides n plus 1 times n plus 2 times n plus 3. And if it divides n plus 2, it divides n plus 1 times n plus 2 times n plus 3, right, because it divides that piece. And if it divides n, then 3 divides n plus 3, because it's just whatever goes into n one more time. And so 3 divides again n plus 1, n plus 2, n plus 3. And so in any of the 3 possible cases, 3 divides this product, and therefore you got p of n plus 1. And then you throw your induction there. The other way to solve this kind of problem is with modular arithmetic. Because if you start off with your number n and you just work mod 3, and there's no induction involved in this, you've got 3 cases. 1, n is congruent to 1, 2, n is congruent to 2, 3, n is congruent to 0. If n is congruent to 1, n plus 2 is congruent to 3, which is congruent to 0, and so it's divisible by 3. If n is congruent to 2, n plus 1 is congruent to 3, so it's divisible by 0. And if n is congruent to 0, then n itself is congruent to 0. And so if n plus 2 is divisible by 3, then 3 divides n plus 2, n plus 1, n. And same thing in these other cases. So different ways to get there. All right, so Monday, I want to start talking, so work on your homework, and we'll go over that on Monday. But then I want to start talking about combinatorics, and we're going to start with counting. 1, 2, 3, 4, 5, 6, just counting. And counting is one of those things that we know how to do, but we can get us into some really interesting results and some powerful principles, including something called the Pigeonhole Principle. And so that's what we'll start with, and then we'll move into combinations and permutations and probabilities and things like that. That'll take us through next week. The following week, 10, is short. We only meet on Monday because we've got our break at the end of the week. But we'll probably wrap up counting and recursion, and the last week, 11, we'll deal with automata and languages and grammars. And that'll pretty much do us.
Why is the 10th week short?
Thanksgiving break.
Thanksgiving.
Yeah. All right, so I will see you